Look up at the night sky. What do you see? A vast, tranquil ocean of stars, each one a tiny pinprick of light in the endless dark. But hidden among them are cosmic giants so massive, so bizarre, they defy everything we think we know about how stars behave. These are supermassive stars, colossal furnaces of energy, some weighing hundreds of times more than our Sun, burning with such intensity that they warp the very fabric of space around them. And yet, for all their grandeur, they're also some of the most enigmatic objects in the universe. Astronomers have spent decades studying them, and still, these celestial titans keep revealing behaviors so strange, so utterly unexpected, they leave even the brightest minds scratching their heads. What could possibly make a star flicker like a candle in the wind, or vanish for years, only to reappear without warning? How can something so massive spin so fast it nearly tears itself apart? And why do some of these stars seem to defy the laws of physics altogether? The answers lie in a realm where gravity bends light like taffy, where magnetic fields wield unimaginable power, and where the rules we take for granted simply don't apply. This isn't just astronomy, it's a front-row seat to the universe's greatest unsolved mysteries. That's exactly what we're diving into today. Over the course of this journey, we'll uncover 30 of the most bewildering behaviors of supermassive stars, each one a puzzle waiting to be solved. From stars that erupt without warning to ones that dance in perfect sync millions of miles apart, these phenomena challenge our understanding of the cosmos in ways that are as thrilling as they are humbling. So buckle up, because by the time we're done, you'll never look at the night sky the same way again. The universe is stranger than we ever imagined, and it's time to explore why. Imagine a star so unpredictable, it flickers like a faulty light bulb, not in a steady rhythm, but in chaotic bursts that leave astronomers baffled. This is exactly what happens with certain supermassive stars, where brightness fluctuations defy every textbook model of stellar behavior. One moment they blaze with the intensity of a cosmic lighthouse, the next they dim so dramatically you'd think they were on the verge of vanishing. These aren't the predictable pulsations of a variable star, these are erratic, almost temperamental shifts that suggest something far stranger is at play. So what's causing this cosmic light show? One leading theory points to internal instabilities, violent churns deep within the star where unimaginable pressures and temperatures create pockets of turbulence. Picture a pot of water boiling over, but on a scale where the bubbles are larger than entire solar systems. These colossal energy surges might push material outward, briefly blocking the star's light before collapsing back in, creating those wild brightness swings. But there's another possibility lurking in the shadows: hidden companions. Some supermassive stars might not be solo acts at all. An unseen partner, perhaps a smaller star or even a black hole, could be orbiting so close that its gravitational tug distorts the primary star's shape, warping its light output. Every time this cosmic dance partner swings by, it might siphon off material or trigger eruptions, making the star's brightness yo-yo unpredictably. Here's where it gets even weirder: some of these stars don't just flicker, they vanish for years before roaring back to life. Astronomers have cataloged cases where a supermassive star dims beyond detection, only to reappear decades later, as if nothing happened. Could these be signs of colossal stellar quakes, or evidence of vast dust clouds suddenly condensing around the star? The truth is, we're still piecing together the clues. What's certain is this: when it comes to supermassive stars, even the simplest question, why does it flicker, can lead us into the deepest mysteries of the universe. Now picture this: a star hurtling through the void at millions of miles per hour, moving so fast it could cross the length of a galaxy in just a few million years. These aren't rogue planets or wandering comets, these are hypervelocity stars, cosmic projectiles ejected from their homes with enough force to escape the gravitational pull of an entire galaxy. And the most mind-bending part, The very thing that flings them into the void might be the last place you'd expect a supermassive black hole. Take the star known as S5HVS1, for example. This runaway stellar bullet was clocked racing through the Milky Way at over 1.5 million miles per hour, so fast that it's on a one-way trip out of our galaxy. How does something like that even happen? The leading theory involves a cosmic slingshot effect near the supermassive black hole at the center of the Milky Way. Imagine three stars locked in a tight dance near the black hole's event horizon. If one gets too close, the black hole's gravity can capture it, while the other two get flung outward at impossible speeds. It's like a game of interstellar pinball, where the loser gets swallowed and the winners are launched into the void. But hypervelocity stars aren't just fascinating oddities, they're also galactic messengers. By tracing their paths backward, astronomers can map the hidden forces at work in the hearts of galaxies. Some of these stars even carry chemical signatures hinting at their origins, like cosmic breadcrumbs leading back to their violent births. And then there are the real outliers, stars like LP44, moving so fast they shouldn't exist at all. Their speeds defy even the black hole slingshot model, suggesting something even more exotic might be at play, perhaps a supernova explosion gone asymmetrically wrong, or a close encounter with a runaway black hole. The strangest part, these hypervelocity ejections aren't just tearing stars away from their homes, they're reshaping entire galaxies. Every time a massive star is flung into intergalactic space, it takes potential new solar systems, even life-bearing planets with it. Some researchers speculate these cosmic escapees could be seeding the universe with the building blocks of life, scattering stardust far beyond their birthplaces. So the next time you gaze up at the night sky, remember somewhere out there, a star is racing into the darkness, carrying secrets we're only beginning to uncover. Deep within certain supermassive stars lies a hidden force so powerful, it can twist the fabric of space itself, magnetic fields stronger than anything we've ever measured. We're not talking about the gentle pull of a refrigerator magnet or even the intense fields around neutron stars. These are cosmic dynamos, generating magnetism so intense it could rip atoms apart from thousands of miles away. Take the star HE45166, for example. Its magnetic field clocks in at over 1,000 times stronger than Earth's, bending light and warping the very particles swirling around it. Where does such unimaginable power come? The leading explanation points to a phenomenon called dynamo theory, but on a scale that dwarfs anything in our solar system. Picture the star's core, a churning ocean of superheated plasma where charged particles spiral at nearly the speed of light. As these particles collide and twist, they generate electric currents, which in turn produce magnetic fields. Normally, these fields would balance out, but in supermassive stars, the sheer volume of plasma and the star's rapid rotation amplify the effect exponentially, like a cosmic generator stuck in overdrive. The consequences are anything but subtle. These magnetic monsters don't just influence their immediate surroundings, they sculpt entire regions of space. Some stars develop colossal loops of magnetic energy, arcs so vast they could stretch from the Sun to Saturn. When these loops snap, a process called magnetic reconnection, they release bursts of energy equivalent to 1 billion atomic bombs. And then there are the truly bizarre cases, like Tau Scorpii, where the magnetic field isn't just strong, it's lopsided. One side of the star might have a magnetic grip 10 times stronger than the other, creating a strange asymmetrical force field that baffles astronomers. But perhaps the most unsettling effect of these magnetic behemoths is how they distort time itself. Einstein's theory of relativity tells us that intense gravity can warp spacetime, but extreme magnetism can do something eerily similar. Near the poles of these stars, charged particles spiral along magnetic field lines with such energy that they effectively slow down time for observers watching from afar. It's as if the star's magnetism doesn't just bend space, it twists the very rules of reality. For all their destructive potential, these magnetic fields might also be cosmic lifelines. Some researchers speculate they could shield fledgling solar systems from deadly radiation, creating safe zones where planets might form. Others suggest they might even funnel energy into interstellar space, sparking star formation light years away. Whatever the truth, one thing's certain: when a supermassive star flexes its magnetic might, the universe pays attention. Some of the most violent stellar eruptions don't blaze in visible light, they scream across the cosmos in X-rays, bursts of energy so intense they can outshine entire galaxies. These aren't the steady glows of a star's corona or the predictable pulses of a binary system. They're sudden, violent eruptions and cosmic screamers that defy explanation. Take Eta Carinii, for instance. This supermassive star occasionally unleashes X-ray flares so powerful they'd vaporize a planet at the distance of Mars, all while remaining eerily quiet in the visible spectrum. The mystery deepens when you realize these outbursts don't match any known stellar process. Typical X-ray sources, like neutron stars or black hole accretion disks, produce radiation in predictable patterns. But these supermassive stars emit X-rays in chaotic spasms, sometimes years apart, sometimes in rapid succession. One leading theory suggests colossal magnetic reconnection events, where twisted field lines suddenly snap like overstretched rubber bands, converting pent-up energy into a single catastrophic release. Picture snapping a giant galaxy-sized whip. The crack at the tip would reach temperatures of millions of degrees, producing those searing X-rays. Then there's the collision hypothesis. Some astronomers propose these bursts occur when dense stellar winds, outflows of gas moving at several million miles per hour, crash into each other or surrounding debris. At such unimaginable speeds, these collisions would act like cosmic particle accelerators, superheating gas until it emits X-rays. But here's the catch: we've observed stars erupting in X-rays even during periods of relatively calm wind activity. It's as if the star has multiple hidden triggers for these explosions, and we've only begun to catalog them. Perhaps the most unsettling possibility involves hidden stellar companions. Many supermassive stars exist in binary systems with smaller, dimmer partners we can't easily detect. If one of these companions is a neutron star or white dwarf, periodic interactions could spark X-ray fireworks. Imagine a neutron star plowing through the outer layers of its massive neighbor, scooping up material that then detonates in thermonuclear firestorms as it hits the neutron star's surface. These microquasars could explain some bursts but not all, leaving astronomers still searching for answers. What's truly remarkable is how fleeting these events are. Unlike supernova that shine for weeks, these X-ray bursts often last mere hours, sometimes minutes. Catching one in action requires telescopes to be looking at exactly the right place at exactly the right time. It's like trying to photograph lightning in a pitch-black forest while blindfolded, yet each detection teaches us something new about the extreme physics governing these stellar behemoths, and reminds us how much we still have to learn about the universe's most volatile giants. In the cosmic dance of life and death, most stars follow a predictable script: burn bright, expand, and then collapse in a final, spectacular supernova. But a rebellious few refuse to bow out gracefully. These are the universe's ultimate survivors, stars so stubborn they cheat death itself. Meet the zombie stars, celestial anomalies that endure supernova only to keep shining, defying every rule we thought governed stellar evolution. Take Eta Carinii, a star so massive and unstable it should have torn itself apart centuries ago. In the 1800s, it erupted in a false supernova, blasting enough material into space to form 10 copies of our solar system. Astronomers of the era watched in awe as it briefly became the second brightest star in the sky, then faded, but didn't vanish. Somehow, against all odds, it held on. Today, Eta Carinii still burns, wrapped in the ghostly nebula of its own near-death experience, a cosmic phoenix that refuses to be extinguished. What keeps these stellar zombies alive? One clue lies in their bizarre structure. Unlike normal stars which fuse elements in orderly layers, supermassive stars like Eta Carinae often churn like boiling water, mixing elements chaotically throughout their cores. This turbulent interior might create pockets of stability that prevent total collapse, acting like emergency brakes on a runaway train. Even as parts of the star detonate, others cling on, creating a patchwork of destruction and survival that leaves astronomers scratching their heads. Then there's the case of IPTF-14s, a star that didn't just survive one supernova, it exploded again and again over 50 years, like a cosmic jack-in-the-box. Most supernovae fade after weeks, but this star kept erupting in pulses, each outburst nearly as bright as the last. The leading theory, a Russian doll scenario where the star's core is so massive it collapses into a black hole while outer layers continue fusing material, triggering repeated explosions. It's as if the star can't decide whether to live or die, stuck in a perpetual state of stellar limbo. Perhaps most unsettling is how these undead stars rewrite the rules of stellar life cycles. Conventional models suggest supermassive stars must die young, their immense weight crushing them into black holes or neutron stars, yet zombie stars linger, suggesting our understanding of stellar physics might be missing a crucial chapter. Some researchers speculate these survivors might even seed the universe with rare elements forged in their turbulent cores, spreading heavy metals across galaxies in their defiant death throes. For all their mystery, one thing is certain: when a star refuses to die, it forces us to question everything we thought we knew about the life and death of cosmic giants. And somewhere out there, right now, another stellar zombie might be preparing its next act in this grand, enigmatic cosmic drama. Most stars spin, our own sun rotates once every 25 days, but some supermassive stars take this motion to an extreme, whirling so fast they stretch into cosmic pancakes. These rapid rotators defy the laws of physics as we know them, spinning so close to their theoretical breakup speeds that a single nudge could send them flying apart. Take VFTS-102 in the Tarantula Nebula, for instance, a star so massive it weighs 180 times our Sun, yet completes a full rotation in under 24 hours. At that speed, its equator bulges outward, flattening the star into an oblate shape like a beach ball squeezed at the poles. The forces at play here are nothing short of terrifying. Centrifugal force, the same effect that sends water flying off a spinning umbrella, rips at the star's outer layers, flinging material into space at millions of miles per hour. Some of these stars shed entire solar systems worth of mass each year, creating glowing halos of ejected gas that shimmer around them like cosmic auroras. Yet despite this violent shedding, they don't slow down. How? The answer might lie in their internal dynamics. Unlike smaller stars where rotation slows over time due to magnetic braking, supermassive stars may have convective cores that act like giant flywheels, constantly transferring angular momentum outward to keep the outer layers spinning at breakneck speeds. Then there's the mystery of their birth. Stars this massive shouldn't be able to form with such rapid spins in the first place. Their collapsing gas clouds should fragment under the strain. One provocative theory suggests mergers, two already fast-spinning stars colliding and combining their angular momentum into a single, dizzying powerhouse. Imagine two figure skaters clasping hands mid-spin, their combined rotation becoming a blur. Now scale that up to stellar proportions, and you've got a recipe for the universe's most extreme centrifuges. But the real shocker, some of these stars might be spinning themselves invisible. At certain angles, their equatorial bulges grow so pronounced that they effectively eclipse their own poles from view, creating bizarre light variations as they rotate. Others develop gravity-darkened equators, regions where the outward force weakens surface gravity, cooling the gas just enough to dim its glow. The result: a star that looks radically different depending on whether you're viewing it pole on or edge on, challenging astronomers to decipher what's truly happening beneath the chaos. Perhaps most unsettling is what these speed demons tell us about stellar limits. Physics textbooks once claimed stars couldn't exceed about 500 kilometers per second at the equator without disintegrating, yet supermassive scofflaws like 893129, a blast past that barrier, clocking in at over 6. How they cling together remains one of astrophysics' great puzzles. Some researchers speculate their immense magnetic fields act like cosmic corsets, containing the chaos just enough to prevent total annihilation. Others wonder if we're witnessing the precursors of gamma-ray burst stars so unstable their final moments could light up the universe in a blaze of glory. One thing's certain, in a cosmos where most stars move with stately grace, these whirling dervishes remind us that the universe still loves to break its own rules. And somewhere out there, right now, another cosmic spinner might be pushing the limits even further, teetering on the edge of existence itself. Among the most baffling cosmic oddities are stars that defy the standard recipe of stellar chemistry. While most stars follow predictable patterns in their elemental makeup, hydrogen and helium dominating, with traces of heavier elements, some supermassive outliers flaunt compositions so strange they rewrite the rules of stellar evolution. Take the carbon stars, for instance. These celestial anomalies drown in so much carbon that their atmospheres resemble cosmic soot factories, shrouding them in thick veils of graphite and complex molecules. In a universe where oxygen typically outweighs carbon, these stars invert the formula entirely, as if someone flipped the cosmic periodic table upside down. How does a star become so carbon-rich? The answer lies in a process called dredge up, where convection currents deep within the star drag carbon forged in the core up to the surface. But in normal stars, this process is slow and orderly. In these carbon monsters, something turbocharges the effect. One theory points to binary companion smaller stars that steal helium from their massive neighbors, triggering runaway nuclear reactions that overproduce carbon. Another suggests these stars might be stellar vampires, cannibalizing carbon-rich material from surrounding space. Either way, the result is a star that essentially turns itself into a floating diamond mine, with conditions so extreme they've even spawned bizarre carbon-based molecules never seen naturally on Earth. On the opposite end of the spectrum are the iron-deficient stars, cosmic ghosts with barely a trace of heavy elements. Most stars inherit their metal content from the gas clouds that birth them, but these outliers somehow formed in near-perfect voids, as if they were born in a universe that hadn't yet learned to forge metals. The star He-24-0259 is a prime example. It contains less than 100,000th the iron of our Sun, making it a pristine relic from the early cosmos. Finding such a star in today's metal-polluted universe is like stumbling upon an untouched glacier in the middle of a desert. What's truly puzzling is how these metal-poor stars can exist alongside their carbon-rich counterparts in the same regions of space. Some astronomers propose they're intergalactic immigrant stars, flung into the Milky Way from dwarf galaxies that never had much metal to begin with. Others speculate they might be second-generation stars, formed from the ashes of the very first supernova, which produced scant amounts of iron. Either way, their presence forces us to reconsider how elements spread or failed to spread in the young universe. Then there are the real chemical rebels, stars with lopsided compositions, where elements like lithium or europium appear in concentrations that defy all models. Some show bizarre isotopic ratios, hinting at exotic nuclear processes we've yet to understand. Others contain radioactive elements like technetium, which has a half-life of just a few million years, proof that these stars are actively forging rare elements in their cores right now. It's as if each of these stellar mavericks is running its own private alchemy lab, cooking up elements in ways that leave even the sharpest astrophysicists bewildered. The implications reach far beyond curiosity. These chemical anomalies might hold the keys to understanding how the universe distributed the building blocks of planets and life itself. After all, every atom in our bodies was once forged in a star. If some stars specialize in oddball chemistry, they could be seeding the cosmos with ingredients for worlds unlike anything in our solar system. Who knows what strange planets might form around a carbon star, worlds with mountains of graphite, oceans of tar, or skies filled with carbon-based rain. The possibilities are as endless as they are alien, and somewhere out there, another chemically bizarre star is waiting to be discovered, ready to challenge our assumptions once again. Picture two stars locked in a gravitational embrace so intimate they breathe as one, cosmic twins sharing not just an orbit, but their very atmospheres. These are contact binaries, supermassive stars whose outer layers have merged into a swirling, turbulent bridge of plasma. Unlike ordinary binary systems where stars dance at a respectful distance, these stellar pairs are practically spooning, their surfaces so close that gas streams between them in a continuous, chaotic exchange. The result, a relationship so volatile it makes soap operas look tame. Take VFTS 352 in the Tarantula Nebula, a pair of blue giants so tightly bound they complete an orbit in just over 1 day. Each star weighs nearly 30 times more than our Sun, yet they're separated by less than 5 million miles, close enough that tidal forces have stretched them into egg-shaped monstrosities. Their shared atmosphere churns with temperatures exceeding 50,000 degrees, creating a feedback loop of stellar winds that strip material from one star and hurl it onto the other. It's a cosmic tug-of-war where both sides are losing, spilling enough mass every century to build a planet. What happens when stars share this much chaos in the most spectacular sense? The transfer of material between them isn't gentle, it's a tempest of superheated plasma, sparking violent flares and eruptions that defy prediction. Some systems, like Beta Lyrae, exhibit brightness swings so extreme they were mistaken for variable stars for centuries. But the real fireworks begin when one star starts siphoning hydrogen from its partner like a celestial vampire. This stolen fuel can trigger runaway nuclear reactions on the thief's surface, leading to periodic explosions called nova events, thermonuclear detonations powerful enough to outshine entire galaxies for weeks. Yet even these pyrotechnics pale next to the system's ultimate fate. As the stars spiral closer, their mutual gravitational pull distorts spacetime itself, emitting ripples that carry away orbital energy. In a few million years, a blink in cosmic time, they'll either merge into a single, even more massive star or collapse into a black hole binary, their death throes potentially unleashing a gamma ray burst visible across the universe. The strangest part, these tangled twins might be factories for cosmic oddities. Some astronomers speculate their turbulent interiors could forge rare elements like gold and platinum in abundances impossible for solitary stars. Others suggest their explosive interactions might seed surrounding space with organic molecules, sprinkling the building blocks of life across star-forming regions. One thing's certain: when stars share this much, they don't just rewrite their own fates, they change the universe around them. Most stars lose mass gradually, their outer layers drifting away in steady stellar winds, but some cosmic giants play by different rules. These temperamental behemoths hold onto their material for years, even centuries, then suddenly erupt in cataclysmic tantrums, blasting entire planets' worth of matter into space without warning. At the top of this unpredictable class sits Betelgeuse, the red supergiant in Orion's shoulder, a star famous not just for its impending supernova, but for its bizarre habit of coughing up gargantuan globs of plasma without rhyme or reason. Take the Great Dimming event of 2019. Over just a few months, Betelgeuse faded by nearly 2/3, its usual fiery glow reduced to a faint ember. Astronomers scrambled to explain the phenomenon. Was this the star's death throes beginning? The truth proved even stranger. High-resolution images later revealed Betelgeuse hadn't dimmed because it was dying, it had literally spat out a cloud of dust so vast, it temporarily eclipsed itself. We're talking about a stellar belch containing roughly twice the mass of our Moon, hurtling outward at over 200,000 miles per hour, And here's the kicker, this wasn't some isolated incident. Betelgeuse has a history of these outbursts, with historical records suggesting similar dimming events centuries ago. What triggers such violent expulsions? The leading theory involves colossal convection cells, bubbles of plasma larger than Earth's orbit that rise from the star's interior like boiling water in a pot the size of the solar system. Normally, these bubbles release energy relatively smoothly, but in supermassive stars, they can become trapped beneath the surface by overlying layers, building pressure until, like a champagne cork flying off, they explosively decompress. Picture a geyser on steroids, where instead of water, it's superheated gas with the mass of a small planet, but Betelgeuse isn't alone in this erratic behavior. Yellow hypergiants like Rho Cassiopeiae take mass loss to even more extreme levels. In 2000, this star ejected about 10,000 Earth masses in a single outburst, an event so violent it briefly outshone the rest of the star's emissions combined. Unlike Betelgeuse's dusty expulsions, hypergiants often shed material in strange, semi-transparent shells that linger for decades, creating nested layers of debris like a cosmic onion. The real mystery, these outbursts don't follow any predictable schedule. Some stars go centuries between eruptions, others, like Vuicanes Majoris, seem to be in a near-constant state of upheaval, with tangled knots of ejected material stretching far enough to swallow Saturn's orbit 10 times over. Astronomers have even spotted stars where these episodic mass loss events appear to trigger chain reactions, one ejection destabilizing the outer layers, leading to another, and another, like a stellar version of dominoes. Perhaps most intriguing is what these tantrums reveal about stellar death. Conventional wisdom says massive stars shed their outer layers gently before going supernova. But these episodic outbursts suggest some stars might essentially explode in installments, blowing off chunks of themselves piecemeal before the final curtain call. It's a discovery that's forced astrophysicists to rethink how the most massive stars prepare for their grand finales, and somewhere out there, another supergiant might be gathering its strength for its next cosmic cough, ready to remind us just how unpredictable the universe can be. Among the most dramatic cosmic fugitives are stars flung from their homes at velocities so extreme they can escape entire galaxies, stellar outlaws on one-way journeys into the void. These runaway stars don't just drift away, they're catapulted with enough force to overcome the gravitational pull of their birth clusters, often reaching speeds exceeding 1 million miles per hour. While most stars move in orderly orbits around galactic centers, these renegades streak through space like bullets, leaving behind everything familiar in a desperate bid for freedom. One of the most famous examples is Aorigui, a blue hot star blazing through the constellation Auriga at nearly 200 kilometers per second. What makes this cosmic speedster fascinating isn't just its velocity, it's the trail of clues pointing to its violent origins. By tracing its path backward, astronomers discovered it lines up perfectly with the Orion Nebula cluster, suggesting it was ejected roughly 2.5 million years ago in a gravitational showdown. The likely culprit, a close encounter with a binary star system, where the intruding star got too close and was flung away like a stone from a sling. But gravitational slingshots aren't the only way stars go rogue. Some receive their staggering kicks from supernova explosions, cosmic shoves so powerful they can launch surviving companions into the abyss. Picture a binary system where one star detonates asymmetrically, the blast acting like a rocket engine that propels its partner outward. The star Zeta Ophiuchi tells this exact story, racing through space at 67 kilometers per second, surrounded by a bow shock of compressed gas that betrays its explosive past. Infrared observations reveal it's plowing through interstellar dust like a ship's prow, creating ripples that glow with the energy of its violent escape. The most extreme runaways, however, might owe their speed to supermassive black holes, Near the Milky Way's core, stars can be accelerated to phenomenal velocities by the black hole's tidal forces, some even reaching hypervelocity status, destined to leave the galaxy entirely. Calculations suggest these ejections require intricate three-body interactions, where a star ventures too close to a binary black hole system. One star gets captured, while the other is flung away with enough energy to defy galactic gravity forever. What happens to these exiled stars? Some, like US 708, are already on galactic escape trajectories, future intergalactic wanderers that will drift between galaxy clusters for eternity. Others might collide with molecular clouds, triggering new star formation in their wake. A rare few could even carry planetary systems with them, frozen worlds orbiting a star with no stellar neighbors for millions of light years. Yet the real intrigue lies in what runaways teach us about unseen forces. By studying their trajectories, astronomers can map hidden gravitational disturbances, whether from past supernova, black holes, or even dark matter interactions. Each runaway star is a cosmic detective story, its path encoding secrets about the violent events that shaped it, and as telescopes grow more powerful, we're finding these stellar fugitives are far more common than anyone imagined, proof that even in the vastness of space, chaos leaves its mark everywhere. Every star has an expiration date, especially supermassive ones, destined to end their lives in spectacular supernova explosions, but some cosmic giants refuse to follow the schedule, lingering for thousands, even millions of years past their theoretical demise. Imagine a ticking time bomb that keeps resetting its own clock, defying the laws of physics with every passing second. That's exactly what astronomers observe in stars like N694, a supermassive star in the small Magellanic Cloud that's been about to explode for decades, teasing researchers with erratic flickers while stubbornly clinging to existence. What causes these cosmic procrastinations? The answer might lie deep within the star's turbulent heart. Traditional models assume supernova occur when a star's core collapses under its own weight, a straightforward process that should take mere seconds once triggered. But recent observations reveal some stars engage in a bizarre form of stellar CPR, where collapsing material rebounds with unexpected force, reigniting nuclear fusion and temporarily staving off total collapse. It's like a skyscraper that starts collapsing, only for its supports to suddenly snap back into place at the last possible moment, a phenomenon so counterintuitive it's rewriting our understanding of stellar deaths. Then there's the zombie fuel theory. Some supermassive stars might harbor hidden reservoirs of helium or carbon in their outer layers, material that gets dredged up and reignited just as the core begins failing. This backup energy source could pump fresh life into the star, delaying its explosion in fits and starts. Evidence comes from stars like IPTF-14s, which experience multiple violent eruptions over 50 years instead of a single, decisive explosion. Like a dying fire that flares up one last time when stirred, these stars seem to find brief reprieves where none should exist, but the most intriguing delay mechanism involves something even more exotic: quantum oddities in the star's core. At extreme densities, subatomic particles called neutrinos, normally ghostly particles that slip through matter unimpeded, might get trapped in the collapsing core, creating a pressure buffer that slows the star's death spiral. Supercomputer simulations show this neutrino traffic jam could buy the star precious extra time, stretching what should be a seconds-long collapse into days or weeks of false starts. It's as if the star's own nuclear physics develops a form of cosmic stage fright, hesitating at the brink of annihilation. The implications are staggering. If supermassive stars can postpone their explosions, it means they might alter their chemical legacy, spreading heavier elements across wider regions of space than traditional models predict. Some researchers speculate these delays could even explain mysterious gaps in the cosmic distribution of certain metals, where galactic chemistry doesn't match supernova timelines. Perhaps most unsettling is what these lingering giants tell us about the limits of stellar physics. Every delayed supernova is essentially a cosmic rebellion, a star refusing to follow the script written by our equations. And as astronomers discover more of these stubborn holdouts, they're forced to confront an humbling truth. When it comes to the deaths of the universe's mightiest stars, we've barely scratched the surface of what's possible. Imagine witnessing a stellar explosion that happened centuries ago, not through some cosmic recording, but in real time, as light from the long-dead star finally reaches us after bouncing off interstellar mirrors. This is the phenomenon of light echoes, where supermassive stars continue to speak from beyond the grave. Take the case of Cassiopeia A, a supernova remnant whose original explosion likely lit up Earth's skies around 1680. While the initial flash vanished long ago, light from that cataclysm still reaches us today, not directly, but as reflections ricocheting off dust clouds light years away. These delayed photons create luminous ripples expanding through space like sound waves echoing in a canyon, offering us a time machine to study the supernova's final moments centuries after the fact. The physics behind these echoes is as elegant as it is mind-bending. When a star explodes, its light spreads outward in all directions at, well, the speed of light. But if some of that radiation encounters dense interstellar dust, tiny particles scatter the photons, sending them on new paths toward Earth. Since these detours are longer than the direct route, the reflected light arrives years or even decades later. The result? A celestial replay where we observe the same explosion multiple times from different angles, like watching lightning strike, then hearing its thunder roll in from valleys miles apart. Some of the most stunning examples come from supernova 1987, A in the Large Magellanic Cloud. While the initial blast faded within months, light echoes continued appearing in concentric rings around the remnant for over 25 years. Each ring represented light that had taken a slightly different path through the cosmic dust maze surrounding the dead star. By analyzing these echoes, astronomers reconstructed the three-dimensional structure of the explosion in unprecedented detail, revealing asymmetrical jets and turbulent plumes invisible in the original event. But light echoes aren't just pretty cosmic quirks, they're forensic tools. The reflected light often carries spectral fingerprints of elements forged in the supernova, allowing scientists to study stellar chemistry without waiting for a fresh explosion. When echoes from the 19th century eruption of Eta Carinii were analyzed, they revealed unexpected traces of titanium and nickel, elements suggesting the star's outburst was far more violent than historical records indicated. Perhaps most astonishing is how these echoes challenge our perception of time in the universe. Right now, light from ancient supernova could be reflecting off dust clouds halfway across the galaxy, carrying messages from stars that died before humans built the first cities. Somewhere out there, photons from Tycho's supernova of 1572 might still be weaving their way toward us, due to arrive centuries from now. It's a humbling reminder that in the grand tapestry of the cosmos, even death isn't the end, just another chapter in a story written in light. Deep beneath the surface of some supermassive stars, pressures build to such catastrophic levels that the entire structure shudders, not with the gentle sway of an earthquake, but with planet-shattering convulsions that send seismic tsunamis racing across their surfaces. These aren't mere tremors, they're starquakes, violent upheavals releasing more energy in seconds than our sun produces in centuries. Take the star K76585111, a yellow hypergiant where astronomers detected ripples so powerful they momentarily brightened the star's entire western hemisphere by nearly 10%. Imagine a quake so colossal it briefly turns night into day across half a star. What triggers these cosmic convulsions? The culprits lie in the star's churning interior. Unlike Earth's crust floating on molten rock, a supermassive star's outer layers rest atop a seething plasma ocean where magnetic fields twist like tangled rubber bands. When these fields snap, or when pockets of trapped radiation suddenly burst free, they unleash shockwaves that ripple outward at millions of miles per hour. Some starquakes originate from deep within the core, where unstable fusion reactions create pressure imbalances akin to a nuclear bomb, perpetually teetering on the edge of detonation. Others stem from the star's rapid rotation, where centrifugal forces stretch its equator until the surface literally cracks under the strain. The effects are anything but subtle. As these seismic waves travel, they distort the star's surface into towering ridges and valleys hundreds of miles high, features that would dwarf Mount Everest in seconds. Satellite observations of the star ER38329 captured one such event, where a quake lasting just 12 minutes temporarily flattened the star's polar regions, altering its shape enough to measurably shift its light output. But the real spectacle happens when these waves reach the surface, launching tsunamis of superheated plasma that splash back down with enough force to trigger secondary quakes, a stellar echo effect that can keep the star trembling for days. Perhaps most bizarre is how starquakes leave behind cosmic fingerprints. Just as earthquakes reveal Earth's inner structure through seismic waves, stellar vibrations betray secrets about a star's hidden layers. By analyzing the frequencies of these oscillations, a technique called asteroseismology, astronomers can essentially ultrasound a star's guts. Some hypergiants even exhibit ringing after major quakes, vibrating at specific tones like a struck gong. The star Vela X1, for instance, resonates at ultra-low frequencies equivalent to a B-flat 57 octaves below middle C, a hum so deep it's inaudible to any human ear, but detectable across interstellar space by sensitive telescopes. These aren't just celestial oddities, they're windows into stellar survival. Some researchers believe starquakes might explain mysterious episodes of mass loss, where supermassive stars suddenly eject shells of material without warning. Others speculate they could trigger runaway nuclear reactions on a star's surface, potentially delaying or even preventing supernova. One thing's certain: when a star shudders, the universe listens. And somewhere out there, right now, another cosmic giant might be gathering the energy for its next great quake, a reminder that even the mightiest stars are never truly at rest. Some stars dance alone, or so we thought. Look closely and you'll find celestial performers whose motions betray invisible partners, their gravitational waltz revealing presences no telescope can see. These aren't ordinary binary systems where two stars pirouette in plain view. These are cosmic phantoms, black holes, neutron stars, or even clumps of dark matter tugging at their visible counterparts with enough force to make entire stars shimmy across the sky like puppets on strings. Take the case of LB1, a blue giant in our galaxy that wobbles with clockwork precision every 79 days. At first glance, nothing nearby explains its rhythmic sway, until calculations revealed an invisible companion weighing at least 70 times our Sun's mass. The only object matching that description, a black hole so stealthy it emits no light, betrayed only by the star's persistent shudder as it's yanked through space. What makes this duo bizarre isn't just their dark partnership, it's that such a massive black hole shouldn't exist under current stellar evolution models. Its very presence forces astronomers to question how these gravitational ghosts form in the first place. Then there's the enigma of HD 199944, a yellow supergiant whose erratic path suggests something even stranger lurking nearby. Instead of neat elliptical orbits, this star jerks unpredictably, sometimes accelerating, sometimes pausing mid-motion like a car with faulty brakes. The leading culprit, a rogue black hole drifting through interstellar space, its chaotic trajectory warping the star's path into a cosmic scribble. Unlike black holes born from collapsed stars, these nomads might be primordial relics from the universe's birth, wandering unseen until they grab a stellar dance partner. But the most unsettling wobbles come from stars influenced by something far more elusive, dark matter. In dwarf galaxies like Triangulum 2, certain stars move as if gripped by massive, invisible hands. their velocities too high to explain with visible matter alone. Some researchers propose these anomalies stem from dark matter clumps, dense knots of the universe's most mysterious substance bending spacetime enough to yank stars off course. If proven, these dark companions would represent an entirely new class of celestial phenomena, one where the unseen doesn't just influence motion, but dominates it entirely. The methods astronomers use to spot these phantoms are as clever as they are indirect, by analyzing starlight for subtle Doppler shifts, the same effect that makes a siren's pitch change as it passes. Scientists can reconstruct a star's velocity changes down to meters per second. Others study astrometric wobbles, tracking a star's precise position until its tiny back and forth motions reveal an invisible partner's mass and orbit. In extreme cases like the star S2 near our galactic center, these minute deviations unveiled Sagittarius as star, the supermassive black hole hiding in plain sight. What's truly remarkable is how many of these dark companions defy classification. Some tugged at stars' orbit, nothing we can detect, no black hole, no neutron star, not even a brown dwarf. One explanation, failed black holes, is stellar corpses that didn't quite collapse into singularities, but instead became ultra-dense, light-swallowing orbs too dim to spot. Others might be quark stars, hypothetical objects squeezing matter beyond neutron star limits into exotic states that absorb all radiation. Every unexplained wobble is a cosmic detective story waiting to be solved. And with new telescopes like the upcoming Vera Rubin Observatory, set to monitor billions of stars for telltale tremors, we're on the verge of uncovering legions of these hidden partners. Some might rewrite the rules of stellar evolution, others could be our first tangible evidence of dark matter's structure, but one thing's certain, wherever a star moves without visible cause, the universe is whispering secrets about the unseen forces pulling its strings. At the poles of certain supermassive stars, nature builds its own particle accelerators, twin beams of plasma so powerful they could sterilize entire solar systems light years away. These aren't gentle stellar winds or random ejections, they're focused jets of death, channeling the star's fury into narrow corridors that pierce space like cosmic blowtorches. The star Eta Carinae demonstrates this phenomenon in terrifying fashion, where opposing jets shoot outward at over 90% light speed, carrying enough energy to outshine most galaxies for brief moments. What makes these jets so extraordinary isn't just their power, it's their precision. Whereas typical stellar outbursts spray material in all directions, polar jets maintain laser-like focus for thousands of astronomical units, punching through interstellar clouds with surgical intensity. The physics behind these beams defies belief. Imagine the star's rotation acting like a cosmic centrifuge, flinging material outward along its equator while intense magnetic fields channel plasma toward the poles. These fields don't just guide the flow, they twist it into helical structures tighter than DNA strands, accelerating particles through mechanisms we still struggle to understand. The result, a beam where protons reach energies millions of times greater than anything produced in human-made colliders. When such a jet from the star SS433 swung toward Earth in 2019, it flooded our upper atmosphere with X-rays powerful enough to distort radio communications across the Pacific, all from a source 15,000 light-years away. Destruction follows these jets like shadows, where they strike molecular clouds. They trigger shockwaves that compress gas into new stars, a stellar genesis born from annihilation. Planets caught in the crossfire don't stand a chance. Observations of the system MWC349 reveal a debris field along its jet's path, the remains of what was likely a gas giant torn apart by relentless particle bombardment. Even more chilling are the fossil jets we found carved into nebulae long, hollow tunnels where some ancient star's beams once scoured the interstellar medium clean, leaving behind ghostly passageways detectable millennia after the star itself perished. Perhaps most bewildering is how these stellar quasars scale down galactic phenomena to personal proportions. The mechanisms resemble those powering active galactic nuclei, just compressed into a volume billions of times smaller. It raises provocative questions. Could some mini-jets we observe actually be full-sized ones from impossibly distant galaxies, magnified by gravitational lensing? And what does it mean when a single star can mimic, however briefly, the most violent engines in the cosmos? The implications stretch beyond destruction. Some theorists suggest these jets might seed galaxies with heavy elements normally trapped in stellar cores, acting as cosmic hypodermics, injecting enriched material directly into star-forming regions. Others speculate they could influence galactic magnetic fields on scales far exceeding the star's physical reach. Whatever their role, one truth remains: when a supermassive star aligns its poles with our line of sight, we're witnessing nature's most focused fury, a reminder that even in the vastness of space, energy prefers the path of least resistance, even if it means drilling through reality itself. Beneath the seething surfaces of supermassive stars, nuclear reactions occasionally reach a breaking point, not in the controlled fusion of their cores, but in violent detonations that blast newly forged elements straight into space like cosmic indigestion. These aren't gentle stellar winds or gradual mass loss, they're full-scale thermonuclear belches, eruptions so violent they can temporarily outshine the star itself. Consider the yellow hypergiant Rho Cassiopeiae, which in 2001 ejected a shell of material containing 10,000 times Earth's mass, enough to build 30 planets like Jupiter, in an outburst lasting just a few months. The expelled gas wasn't just surface material either. Spectra revealed it was laced with titanium and rare earth metals, proof the explosion had dredged up elements cooked deep in the star's nuclear furnace. The mechanics behind these eruptions rewrite the rules of stellar behavior. Normally, energy from fusion reactions diffuses outward slowly, taking thousands of years to reach the surface. But in certain supermassive stars, convection can become so turbulent it creates shortcuts, columns of rising plasma that act like freight elevators, hauling superheated, freshly fused material straight to the surface. When this enriched gas hits cooler outer layers, the temperature differential triggers runaway nuclear reactions. Think of gasoline vapor igniting as it meets open air, but on a stellar scale. The resulting detonations don't follow the orderly chain reactions of hydrogen bombs, they're more like poorly stored fireworks going off in cascades, with each explosion destabilizing neighboring regions. What makes these events truly bizarre is their unpredictability. Unlike supernova that signal their impending doom with neutrino bursts, or variable stars that pulse on strict schedules, these thermonuclear belches strike without warning. The star VX Sagittarii once remained quiet for 60 years before suddenly expelling a magnesium-rich plume at 4% light speed, a projectile so massive it briefly formed its own reflection nebula. Other stars, like Betelgeuse, seem to build toward eruptions in stages, first dimming as huge bubbles of gas rise to the surface, then brightening explosively when these bubbles rupture. The chemical fingerprints left by these outbursts are rewriting galactic chemistry textbooks. Normally, heavy elements like strontium or yttrium remain trapped in stellar cores until supernova explosions scatter them. But thermonuclear belches appear to skip the queue, ejecting these metals prematurely in discrete packages. Some researchers speculate this could explain mysterious pockets of rare elements found floating between stars, calling cards from ancient eruptions we missed witnessing directly. Perhaps most unsettling is how these events blur the line between eruption and explosion. Some hypergiants experience superbelches, multi-stage events where initial ejecta collide with older debris, creating secondary shock waves that ricochet back into the star, triggering even more violent follow-up eruptions. It's a feedback loop of stellar indigestion that could theoretically persist for centuries, turning what we thought were single cataclysms into drawn-out ordeals. And somewhere out there, another supermassive star might be gathering the nuclear ingredients for its next great cosmic burp, ready to remind us that even the universe's mightiest engines can have serious indigestion. In the realm of supermassive stars, gravity isn't always the ultimate authority. Some celestial giants wield magnetic forces so dominant they literally suspend the laws of physics. Imagine a star where the crushing weight of outer layers doesn't collapse inward, but instead floats effortlessly in midair, held aloft by invisible magnetic hands. This isn't science fiction, it's the reality of stars like Sigma Orionis E, where magnetospheres punch so far above their weight class that they sculpt entire atmospheres into levitating rings and disks, like cosmic hula hoops spinning in defiance of nature's pull. The secret lies in magnetic fields strong enough to rewire a star's very architecture. Normally, gravity presses a star's atmosphere close to its surface, but when magnetic forces reach critical strength, often hundreds of thousands of times Earth's field, they push back with enough energy to counterbalance gravity itself. The result: strange suspended structures where superheated plasma doesn't fall or rise, but hovers in perfect equilibrium. In the star 8317, observations reveal a dense equatorial ring floating thousands of miles above the surface, kept aloft by magnetic pressure like a stellar version of Saturn's rings, if Saturn's rings were forged from million-degree gas. What's truly bizarre is how these magnetic traps operate. Unlike ordinary accretion disks where material spirals inward, these levitating zones become cosmic parking lots, regions where atoms get stuck in perpetual limbo, unable to descend or escape. Some stars exhibit dead zones, where trapped plasma stagnates for decades, slowly cooling until it condenses into bizarre metallic vapors never seen in nature. The star Tau Boötis hosts one such anomaly, a shimmering disk of titanium and iron vapors levitating like a floating smelter, its existence defying every model of stellar atmospheric physics. The effects ripple far beyond mere spectacle. These magnetic cages act as stellar laboratories, creating environments so extreme they forge molecules and alloys impossible to replicate anywhere else. Astronomers have detected strange compounds like gaseous chromium monoxide and zirconium nitride in these suspended rings, materials that should instantly decompose under normal stellar conditions. Even more startling are the temperature inversions they create, where layers farther from the star glow hotter than those near the surface, turning thermodynamic textbooks upside down. Yet the real magic happens when these systems go unstable. Every so often, the delicate balance between gravity and magnetism tips, causing entire suspended structures to collapse in cascades of falling fire. The star Theta Aurigui treats us to this drama every few years, when its floating rings suddenly destabilize, raining superheated material onto the surface in fiery avalanches that trigger brilliant flares. It's a stark reminder that even the most elegant cosmic equilibriums are temporary, and when they fail, the universe puts on a light show unmatched by anything humanity could engineer. Perhaps most remarkably, these gravity-defying structures might solve a long-standing cosmic mystery: the origin of certain chemically peculiar stars. Some astronomers speculate that levitating rings could selectively filter elements, allowing lighter atoms to escape while heavy metals accumulate over millennia. This could explain stars like Przybylski's star, which bizarrely concentrates rare Earth elements like promethium and holmium in its atmosphere, as if some unseen sieve were sorting the periodic table in midair. As telescopes grow sharper, we're finding these magnetic marvels are far from rare. They're just exceptionally hard to spot, their subtle signatures often drowned out by stellar glare. But each new discovery peels back another layer of the mystery, revealing a universe where magnetic artistry can, quite literally, lift matter beyond the pull of gravity itself. And somewhere out there, Another star might be spinning its own magnetic magic, hovering the impossible just beyond our view. Nothing on our sun compares to the colossal, wandering shadows some supermassive stars endure, monstrous dark patches that slither across their surfaces like cosmic ink blots, blotting out light with capricious irregularity. These aren't your grandfather's sunspots, they're phantom star spots, temporary blemishes so vast they could swallow Jupiter whole, appearing and vanishing without warning while dragging entire hemispheres into darkness. Take the hypergiant VV Cephei, where astronomers observed a migrating dark region spanning 1/5 of the star's surface, an atmospheric scar so massive it caused the star's brightness to plummet by 20% for months before suddenly dissipating like a bad dream. What makes these shadowy leviathans fundamentally different from ordinary sunspots? The answer lies in their formation. Solar spots arise from concentrated magnetic fields inhibiting heat flow, compact, relatively stable features that follow predictable cycles. But phantom star spots stem from deeper chaos, turbulent plasma, currents surfacing like bubbles in a boiling pot, only to cool rapidly into temporary dark islands. Some researchers believe they're linked to submerged convection zones where material circulates at speeds exceeding 10 million miles per hour, creating whirlpools so violent they dredge up cooler material from unprecedented depths. Picture a hurricane dredging ice from the ocean floor and spreading it across the tropics. That's the scale of atmospheric disruption we're witnessing. The most bizarre aspect, their mercurial migration patterns. While sunspots drift predictably with solar rotation, phantom star spots wander erratically, sometimes stalling for weeks, other times darting across latitudes at speeds that would outpace a hypersonic jet. The supergiant Betelgeuse exhibited this phenomenon spectacularly in 2020, when a colossal dark patch meandered from its equator toward the poles over 8 months, altering the star's shape enough to be detected by interferometry. Even stranger are the ghost clusters, groups of spots that appear synchronously across hemispheres, as if some unseen force were poking fingers into the star from opposite sides simultaneously. These wandering shadows also rewrite the rules of stellar dimming. Unlike planets that transit stars in clean, symmetric dips, star spots create asymmetric light curves with jagged bottoms, like someone took bites out of the brightness graph. Some hypergiants like Mu Cephei display double-dip patterns where brightness rebounds briefly mid-dimming, evidence of complex spot geometries where dark centers are ringed by slightly brighter edges. It's forensic astronomy at its finest, reconstructing invisible surface features from subtle fluctuations in starlight millions of years old. Perhaps most unsettling is how these phenomena challenge our understanding of stellar magnetism. Traditional models can't explain why some supermassive stars develop spots thousands of times larger than magnetic fields should allow, or why certain spots glow faintly in ultraviolet rather than appearing truly dark. The leading theory involves failed flares, aborted magnetic reconnection events that leave behind sprawling, semi-cooled regions resembling cosmic bruises. Others speculate we're seeing the footprints of star-grazing black holes or dark matter interactions, exotic possibilities that remain tantalizingly unproven. Every new detection peels back another layer of mystery. When the European Space Agency's Gaia spacecraft recently catalogued hundreds of supergiants with unexplained dimming events, over half showed patterns suggesting monster star spots rather than dust clouds or companions. It's a growing realization what we once dismissed as observational noise might actually be the fingerprints of these phantom features, dancing across stellar surfaces in rhythms we're only beginning to decipher. And with next-generation telescopes set to map stellar surfaces in unprecedented detail, we may soon discover these wandering shadows are far more than anomalies. They could be the rule rather than the exception for stars living life in the cosmic fast lane. Some stars don't just shine, they feed, draining the very life from their stellar companions in a cosmic display of celestial vampirism. These aren't mere close binaries, they're predator-prey systems where supermassive stars act as gravitational siphon hoses, stripping away outer layers of neighboring stars to fuel their own fiery existences. Consider the case of Beta Lyrae, a binary system where the primary star gorges on its partner so relentlessly that the victim has collapsed into a teardrop shape, its atmosphere stretched into a swirling bridge of stolen plasma, funneling toward its ravenous neighbor at 3 million miles per hour. What makes these cosmic vampires so terrifying isn't just their appetite, it's the bizarre side effects of their feasting. As material spirals from the donor star onto the predator, it forms an accretion disk so dense and hot it often outshines both stars combined. Some systems, like SS-433, exhibit disks where temperatures exceed 50,000 degrees hot enough to vaporize diamonds instantly. The stolen plasma doesn't settle quietly either. It often triggers violent thermonuclear reactions on the predator's surface, creating periodic nova explosions that can briefly outshine entire galaxies. Astronomers call this accretion-induced luminosity, the clinical term for what's essentially stellar force feeding with cosmic fireworks as a side effect. The consequences for the donor star are equally dramatic. What begins as gradual mass loss can cascade into runaway collapse when critical thresholds are crossed. The star V391 Pegasi demonstrates this gruesome transformation. Once a typical main sequence star, it's now a shrunken, helium-rich remnant after losing 90% of its mass to its vampire companion. Some victims don't even get to fade quietly. Systems like Cygnus X1 show stars being torn apart so violently their material forms spiraling jets as it falls toward an awaiting black hole, proving stellar vampirism operates at all mass scales. But here's the cosmic irony: sometimes the vampire gets more than it bargained for. When accretion rates exceed certain limits, the predator star can choke on its stolen meal. The infamous Eta Carinii nearly destroyed itself this way in the 1800s, when excessive mass transfer triggered the Great Eruption, a pseudo-supernova that blasted 10 solar masses into space. Modern simulations suggest this happens when fresh hydrogen reaches the predator's core too quickly, disrupting the delicate balance of nuclear fusion and triggering explosive instability. It's the astrophysical equivalent of overeating until you explode, a cautionary tale written across light years. What fascinates astronomers most are the rejuvenation effects these feedings can produce. Some vampire stars appear paradoxically youthful, their surfaces rich in hydrogen stolen from younger companions, masking their true ages beneath a fresh stellar facade. The star 892607 was caught in this cosmic deception, originally classified as a young blue star, until spectral analysis revealed it was actually an elderly stellar zombie, its outer layers chemically altered by centuries of cannibalizing its neighbor. This discovery upturned traditional methods of stellar age estimation, proving some stars might fake their cosmic ID cards through strategic snacking. The grandest implications might be for how these systems sculpt their surroundings. As vampire stars eject excess material through powerful winds, they seed nearby space with unusual chemical mixes, including elements like lithium that are normally destroyed in stellar cores. Some researchers speculate these systems could be responsible for mysterious lithium-rich stars discovered in globular clusters, stellar vampires spraying rare elements across the cosmos like cosmic graffiti artists. Others suggest their violent interactions might kickstart star formation in neighboring gas clouds, making them unwitting midwives to new stellar generations. From stellar resurrection to catastrophic collapse, these cosmic vampires teach us that in the universe's grand drama, even stars aren't above a little celestial cannibalism, and the consequences ripple far beyond their immediate victims. Every time telescopes spot another teardrop-shaped star or inexplicably young-looking giant, we're reminded that in space, survival often depends on who can steal the most and who can hold on to what's theirs. At the edge of a black hole's crushing gravity, Light doesn't just bend, it slows to a crawl, stretching starlight into eerie, time-warped glows that defy common sense. This isn't mere gravitational lensing, where light curves around massive objects. It's a full-fledged reality distortion, where photons struggle to escape the black hole's temporal quicksand, making entire stars appear to freeze in their death throes. The star S2, orbiting our galaxy's central black hole Sagittarius, a star, demonstrates this phenomenon in stunning detail. As it swings perilously close during its oval-shaped orbit, its light shifts not just to red, but to a bizarre, elongated smear, as if someone hit the universe's slow-motion button. The physics behind these time dilation glows rewires our intuitive understanding of light. Einstein predicted that intense gravity warps time itself. Clocks tick slower near massive objects. Apply this to starlight, and photons emitted near a black hole's event horizon must climb out of a deep temporal well, losing energy in the process. This energy loss isn't just a color shift, it's a literal slowing of perceived time. To an outside observer, the star's final moments before being swallowed might appear stretched across years or even centuries, its light dimming to infrared whispers as time dilation red shifts, its emissions beyond visible detection. Perhaps the most mind-bending implication is how these glows create cosmic illusions. A star that actually plunged into a black hole millennia ago might still appear to hover at the precipice today, its last photons trickling toward us in agonizing slow motion. The black hole's accretion disk might shimmer with phantom stars, ghosts of objects long consumed, their final light still arriving in drawn-out fragments. Telescopes have spotted candidates for these frozen stars, near distant quasars, pinpoints of light that stubbornly maintain position for decades without fading or moving, as if pinned to the edge of oblivion by relativity itself. What makes these observations invaluable is how they let us test general relativity under extreme conditions. By tracking stars like S2, astronomers have confirmed time dilation effects down to a few percent of light speed, matching Einstein's predictions with uncanny precision. Other systems, like the Quasar 3C273, show even more dramatic effects, jets of plasma that appear to move 50 times slower than their actual velocity due to their steep climb out of the black hole's gravitational well. It's like watching a cosmic movie stuck in buffering mode, where reality itself has lagged. The strangest consequence, these time-dilated glows might be our only window into certain black hole mergers. When two supermassive black holes collide, their mind-numbing gravity could trap light from surrounding stars in temporal loops, creating afterimages that linger long after the actual stars are gone. Some theorists speculate this might explain mysterious, slow flares detected near galaxy centers, not true explosions, but the stretched-out final flickers of stars caught in the ultimate cosmic slow-motion reel. Yet for all their elusiveness, these relativistic light shows hold practical value. By analyzing how starlight stretches and reddens near black holes, astronomers can map the unseen, calculating a singularity's spin rate, mass, and even potential quantum fuzziness at the event horizon. Each photon's struggle to escape carries hidden data about the warped spacetime it traversed. In essence, these time dilation glows aren't just optical illusions, they're encrypted messages from the universe's most extreme environments, written in the twisted alphabet of relativity itself. And somewhere out there, another star might be teetering on the edge of a black hole's grip, its light beginning the long, slow slide into timelessness. Among the universe's most puzzling contradictions are supermassive stars that should be cosmic radio beacons yet whisper in silence. Conventional wisdom says colossal stars, with their churning plasma and violent stellar winds, ought to blast radio waves across the cosmos like natural transmitters. But outliers like the yellow hypergiant IRC plus 10-420 defy expectations, emitting radio signals thousands of times weaker than their size and activity should produce. It's as if a roaring jet engine somehow generated no sound, an astronomical paradox that challenges our fundamental understanding of stellar physics, the mystery begins with radio waves' origins in massive stars. Typically, these emissions arise from two sources: thermal radiation emitted by superheated outer layers, and non-thermal synchrotron radiation generated when charged particles spiral through magnetic fields at near light speeds. Stars like Betelgeuse check both boxes, their radio output matching predictions, but radio-quiet giants like Rho Cassiopeae baffle astronomers by lacking both signals simultaneously, as if some invisible filter were blocking their broadcasts. One explanation points to stealthy stellar winds. Normally, fierce winds from supermassive stars collide with interstellar material, creating shockwaves that accelerate particles and amplify radio emissions. But if a star's winds are unusually smooth, lacking the density clumps that typically generate shocks, they might glide through space without the usual radio fanfare. The Hypergeometer 8752 supports this idea. Its radio silence coincides with unexpectedly steady wind patterns detected through ultraviolet spectroscopy. Another possibility involves magnetic field geometry. Most massive stars have tangled, chaotic fields that twist plasma into radio-bright knots, but stars with unusually orderly, large-scale fields might channel their energy differently, like a power station directing electricity away from certain circuits. The B-type star Sigma Orionis exemplifies this. Its strong, rigid magnetic field creates radio-quiet zones despite the star's extreme activity, the most tantalizing hypothesis. Some stars might be cloaked in dense, ionized shrouds that absorb their own radio emissions before they escape. Imagine a fog so thick it swallows sound, but for stars like HD 148937, the fog is a plasma envelope thousands of times denser than models predict, acting as a natural radio jammer. Radio silence isn't just an oddity, it's a clue. These quiet giants might represent rare evolutionary stages where stars temporarily suppress emissions before erupting in violent transitions. Or they could hint at entirely new categories of stellar behavior we've yet to map. Either way, their hush speaks volumes about how much we still have to learn. Some stars glow with more than just visible light. They wear eerie halos of gamma radiation, faint whispers of annihilation flickering around them like spectral shrouds. These aren't the gamma-ray bursts of supernovae or pulsars, but persistent, enigmatic glows that defy conventional stellar physics. Take the massive star LS 539, for instance. While its surface blazes with the expected fury of a blue supergiant, orbiting telescopes have detected a diffuse gamma-ray aura extending billions of miles into space energy signatures matching what you'd expect if dark matter particles were colliding and annihilating deep within its core. The implications are staggering. Scientists have long suspected dark matter might accumulate in dense stellar cores, drawn by gravity like cosmic dust settling in a bowl. But if gamma-ray halos prove this hypothesis correct, we're looking at stars acting as celestial dark matter detectors, natural laboratories where the universe's most elusive substance reveals itself through subtle, high-energy fingerprints. The math is compelling. Stars moving through dark matter-rich regions like those near galactic centers could sweep up weakly interacting massive particles, WIMP over eons. These particles would eventually sink to the star's core, where collisions between matter and antimatter versions would produce gamma-ray photons as their last gasp before vanishing from existence. Not all gamma-ray halos behave the same, though. Some, like the one surrounding the red supergiant Canis Majoris, pulsate in sync with the star's 11-year activity cycle, suggesting dark matter interactions might be modulated by stellar magnetic fields. Others, like the bizarre twin halos around the binary system Eta Carinae, show asymmetrical shapes that hint at complex particle dynamics in turbulent stellar winds. The most perplexing cases are stars like BP Crucis, whose gamma halos contain unexpected, voids, regions where emissions abruptly drop off, as if something were carving gaps in the annihilation process. The hunt for these gamma ghosts is revolutionizing how we study both stars and dark matter. Traditional detection methods rely on underground particle detectors or space observatories searching for indirect signals. But gamma-ray halos offer a third approach, using stars themselves as natural amplifiers, their immense gravity concentrating dark matter to detectable levels. Some researchers even propose stellar seismology. Techniques could detect dark matter's gravitational influence on a star's internal oscillations, providing cross-confirmation of gamma halo observations. Yet mysteries remain. Why do some supermassive stars in dark matter-rich environments lack halos entirely? Could certain stellar compositions or magnetic field configurations suppress particle annihilation? And most chillingly, if dark matter truly is being destroyed in these stellar cores, what does that mean for the universe's ultimate fate? Each faint gamma glow brings us closer to answers, turning the night sky's most brilliant beacons into unwitting guides to the cosmos's darkest secrets. Most stars exhale steadily, their stellar winds blowing outward in predictable streams, like cosmic breath in the freezing void, but supermassive stars cough in fits and starts, their gusts shifting direction so violently they carve ever-changing sculptures into surrounding gas, a celestial sandblaster with a mind of its own. The Wolf-Rayet star WR40 offers a front-row seat to this chaos. Hubble images reveal its winds haven't just blown a nebula, they've twisted it into a spiraling vortex, as if some invisible hand reached down and stirred the cosmos like a cup of coffee. The root of this unpredictability lies in the star's turbulent interior. Unlike our Sun's relatively orderly magnetic fields, supermassive stars churn with plasma currents powerful enough to warp their entire magnetic architecture on a whim. One moment, magnetic field lines might funnel winds preferentially along the star's equator. The next, a subsurface convection bubble erupts, flipping the magnetic poles and redirecting the stellar gale toward the poles instead. The red hypergiant Vui Canis Majoris demonstrates this capriciousness perfectly. Its ejectiform, intricate, cloverleaf-shaped nebulas that change configuration every few decades, betraying unseen battles between competing wind streams deep within the star. These shape-shifting winds don't just create pretty patterns, they forge cosmic construction sites. When opposing wind fronts collide at thousands of miles per second, the shockwaves compress interstellar gas into dense filaments, some heavy enough to birth new stars. The Carina Nebula's Mystic Mountain towers 3 light-year-tall pillars of dust owe their existence to such erratic sculpting, carved by Eta Carinae's moody outbursts over centuries. Elsewhere in the Thor's Helmet Nebula, WR7's vacillating winds have hammered gas into a bubble so perfectly spherical it looks machined, despite originating from pure stellar turbulence. The most bizarre cases occur when winds don't just change direction, they reverse entirely. Astronomers tracking the yellow hypergiant IRC plus 10420 watched in disbelief as its outflow suddenly turned inward for 2 years, sucking previously ejected material back toward the star's surface. The leading explanation involves a temporary magnetic cage collapse, a scenario where the star's restraining magnetic fields buckle, allowing atmospheric pressure to briefly overwhelm the wind's outward push. It's the astrophysical equivalent of a volcano inhaling its own eruption. What makes these stellar mood swings invaluable to science is how they preserve a record of the star's tantrums. Like tree rings encoding past climates, nebula structures around these stars archive centuries of wind shifts. The Egg Nebula's concentric dust shells, for instance, reveal its central star has alternated between polar and equatorial outflows every 150 years like clockwork. Other systems, like the Red Square Nebula, display intricate geometric patterns, X-shapes and diamonds, that only form when winds flip-flop between discrete, preferred axes over millennia. Yet some puzzles remain unsolved. Certain stars, like the blue variable LBV 18620, produce nebulas with bizarre, knotted structures that defy fluid dynamics models. Their winds appear to twist into braids mid-flight, as if guided by unseen magnetic spaghetti. Others exhibit wind shadows, strange, cone-shaped voids downwind of dense clumps, where something blocks the outward flow with uncanny precision. The most promising explanations involve rogue planets or asteroid belts getting vaporized in the stellar gale, their debris creating temporary roadblocks that divert the wind into new configurations. As telescopes grow sharper, we're finding these capricious winds might be more rule than exception for stellar giants. From forging stellar nurseries to rewriting our models of plasma dynamics, their fickle breezes prove that even in the vastness of space, chaos and creativity often go hand in hand. And somewhere out there, another star's winds are shifting direction right now, etching their next masterpiece into the canvas of the cosmos. At the heart of a supermassive star's crushing core, where pressures exceed 1 billion times Earth's atmosphere, the rules of quantum mechanics take center stage, and they don't play by the same script as the tame physics we know. Here in this realm of extreme densities, protons and neutrons jostle so tightly that their quantum behaviors begin orchestrating stellar-scale anomalies, bending reality in ways that ripple outward to the star's surface. Consider neutron stars, the collapsed remnants of massive stars where quantum phenomena like superfluidity and superconductivity dominate. But what if similar quirks emerge in living supermassive stars, subtly distorting their behavior in observable ways? One tantalizing possibility involves quantum tunneling on a stellar scale. Normally, nuclear fusion requires protons to overcome immense electrostatic repulsion, a high-energy barrier. But in ultra-dense cores, quantum tunneling could let protons bypass this barrier more frequently, boosting fusion rates unpredictably. Imagine a star like Eta Carinae, where sudden flare-ups might not stem from classical instability alone, but from quantum-accelerated fusion surges deep within. This could explain erratic luminosity spikes in some hypergiant flares that conventional models struggle to replicate without invoking external factors like companion stars. Then there's the enigma of neutrino transparency. These ghostly particles usually slip through matter unimpeded, but in cores where matter approaches neutron star density, neutrinos might interact just enough to alter energy transport. Simulations of supermassive stars suggest that trapped neutrinos could act like a pressure buffer, temporarily propping up the core against collapse and delaying supernova, a phenomenon that might underlie the zombie star paradox, where certain massive stars linger far past their predicted expiration dates. Even stranger is the potential for quantum entanglement to influence stellar magnetism. If particles in the core become entangled over macroscopic distances, a controversial but theoretically possible scenario, their coordinated spins could amplify magnetic fields to extreme intensities. The star 845166, with its inexplicably powerful magnetic field, might owe its strength not just to classical dynamo action, but to quantum coherent spins spanning kilometers of plasma. Picture billions of particles voting in unison on magnetic orientation, creating a stellar-scale electromagnet that defies traditional limits. Perhaps the most mind-bending speculation involves quantum vacuum effects. In a core where gravitational fields approach black hole intensity, virtual particles popping in and out of existence might get stretched into real particles, releasing bursts of energy. These vacuum fluctuations could manifest as sudden temperature spikes in a star's interior, miniature versions of the unravel effect, where acceleration creates observable radiation. If such events reach the surface, they might produce the mysterious, ultra-short X-ray flashes detected from stars like Rho Cassiopeiae, bursts too brief to arise from conventional thermonuclear processes. Yet detecting these quantum fingerprints remains a monumental challenge. Unlike neutron stars, where quantum effects are laid bare by extreme compaction, supermassive stars cloak their quantum oddities beneath layers of churning plasma. Current telescopes lack the resolution to probe these subtleties directly, but future instruments like the Einstein telescope, a proposed gravitational wave observatory, might sense the ripples from quantum-driven core oscillations. Until then, each anomalous stellar behavior, the flickers, the delays, the magnetic extremes, offers a breadcrumb trail back to the quantum frontier. And every time a supermassive star defies expectations, it whispers a tantalizing question: what if the universe's largest structures are also its most exotic quantum laboratories? Among the universe's most precise light shows are stars that don't just shine, they aim, casting beams so perfectly aligned they pierce the cosmos like celestial searchlights. These aren't random emissions, they're natural lighthouses, where physics conspires to focus starlight into narrow, jaw-droppingly straight columns visible across interstellar distances. Take the Wolf-Rayet star Gamma Velorum, for instance. Its polar jets don't fan out like typical stellar winds, they remain laser-straight for light years, as if some cosmic lens were keeping them perfectly collimated against the chaos of space. The secret lies in a delicate balancing act between rotation and magnetism. Most stars spray energy in all directions, but when a supermassive star spins rapidly while harboring an ultra-strong, neatly organized magnetic field, something extraordinary happens. The field acts like a celestial gun barrel, channeling charged particles into tight streams along the star's rotational axis. Picture water spiraling down a drain, but on a stellar scale, where plasma accelerates to near light speeds along these magnetic highways. The result: twin beams of matter and radiation shooting from the poles with eerie precision, often accompanied by intense X-ray and gamma-ray emissions that flicker like a cosmic strobe. What makes these stellar beacons truly bizarre is their persistence. While human-made lasers scatter over distance, these natural beams maintain their focus far longer than expected. The pulsar PSRB 10958 demonstrates this perfectly. Its particle beam stretches over 150 light-years without dispersing, punching through nebular gas like a needle through fabric. Scientists attribute this to a phenomenon called kinetic focusing, where the beam's own magnetic field self-reinforces, preventing stray particles from escaping sideways. It's as if the universe invented its own fiber optics long before we did, yet the real magic happens when these lighthouses align with Earth. We see them as blazars, objects whose jets point directly at us, creating illusions of superluminal motion and brightness fluctuations that defy intuition. The Quasar 3C273 offers a textbook example. Its jet appears to move 50 times faster than light due to this cosmic sleight of hand, a relativistic mirage caused by particles heading straight our way at 99% light speed. But perhaps the most astonishing aspect is how these beams sculpt their surroundings. Where they strike interstellar clouds, they trigger shockwaves that birth new stars, stellar midwives wielding photon scalpels. Others, like those from the microquasar SS433, carve perfect tunnels through nebular material, leaving behind hollow tubes glowing with synchrotron radiation. It's proof that in the right cosmic conditions, light doesn't just illuminate, it engineers, and somewhere out there, another stellar spotlight might be sweeping across the void, its beam so precise it could be mistaken for intelligence rather than nature's impeccable physics. When two supermassive stars spiral toward each other in a final, catastrophic dance, they don't just collide, they shake the universe itself. These aren't ordinary stellar mergers, they're gravity wave factories, forging ripples in spacetime so powerful they warp the fabric of reality across millions of light-years. The historic detection of GW 150,814 by LIGO, a gravitational wave signal from two merging black holes, opened our eyes to this cosmic phenomenon, but supermassive star collisions take this violence to staggering new levels. creating space-time tremors that could outshine entire galaxies in pure gravitational energy. Picture the final moments before impact. As the stars approach, their immense gravity distorts each other into teardrop shapes, tidal forces stripping away outer layers, while their cores whip around at relativistic speeds. This isn't a graceful waltz, it's a frenzied, asymmetrical tango where the stars don't just orbit but literally plow through each other's atmospheres, creating shockwaves that propagate outward as gravity waves. The resulting spacetime ripples encode the stars' masses, spins, and even their internal composition, a cosmic Morse code broadcast across the universe. What makes these mergers special isn't just their violence, it's their aftermath. Unlike black holes that emit a clean chirp upon merging, supermassive stars often experience prolonged, messy collisions. Some models suggest their partially merged cores can oscillate for minutes or even hours, emitting gravity waves at ever-shifting frequencies, like a cosmic theremin. The star VFT 352, a contact binary with two massive cores already sharing an atmosphere, offers a preview of this process, its impending merger likely to produce gravity waves across a wider frequency band than any LIGO detection to date. These collisions also serve as crucibles for rare cosmic events. The tremendous heat and pressure during merger can trigger exotic nucleosynthesis, forging heavy elements like gold and platinum in quantities dwarfing normal supernova outputs. Some gamma-ray bursts, the universe's most energetic explosions, might originate from these mergers when magnetic fields snap into ultra-relativistic jets during the collision. And the leftover object, whether a hypermassive neutron star or a fledgling black hole, often spins so fast it becomes a pulsar on steroids, beaming radiation across the cosmos. Yet the most intriguing aspect might be how these events probe physics extremes. The gravity waves from a supermassive star merger could reveal whether such objects have quark matter cores where neutrons dissolve into free quarks, or settle the debate on maximum stellar densities. Future detectors like the Einstein telescope could even spot echoes in the signal, potential evidence of quantum spacetime foam near the merged object's event horizon. Each gravity wave detection paints a fuller picture of our universe's most extreme forces, and somewhere out there, another pair of supermassive stars might be beginning their deadly spiral, preparing to send new ripples through the cosmic pond. When they do, the entire universe will tremble. One of the universe's most unsettling disappearing acts occurs when supermassive stars vanish without fanfare, no blinding supernova, no shockwave rippling through interstellar gas, just a star that winks out of existence as if swallowed by the cosmos itself. Astronomers call these events phantom supernova, stellar ghosts that bypass the traditional fireworks of stellar death, collapsing directly into black holes or neutron stars without the cosmic announcement we've come to expect. Take the case of N6946 BH1, a yellow hypergiant in the fireworks galaxy that should have torn itself apart in a cataclysmic explosion visible across 22 million light-years. Instead, over 9 months into the nine, it brightened modestly, just enough to suggest instability, then faded into darkness. Hubble later confirmed the culprit. A black hole had formed where the star once burned, its gravitational pull so overpowering that even light couldn't broadcast its birth. This wasn't a failed supernova, it was a cosmic stealth operation, a star slipping into the shadows without triggering any alarms. So why do some stars opt for this silent exit? The answer lies in a precarious tug-of-war between gravity and nuclear fusion. For most massive stars, core collapse triggers a rebound effect, an outgoing shockwave that rips the star apart in a supernova. But in phantom candidates, simulations suggest the infalling material might overwhelm the shock before it can erupt outward, like a firework dud that fizzles instead of detonating. The star's own weight becomes its executioner, gravity acting as both judge and executioner in one swift motion. The conditions enabling this quiet collapse are chillingly specific. Stars with unusually massive envelopes, thick outer layers of hydrogen and helium, might smother the shockwave before it escapes. Others could owe their stealthy demise to rapid rotation, their swirling cores funneling material inward too efficiently for an explosion to develop. Then there's the wild card, neutrino cooling. In some stars, collapsing cores might emit so many neutrinos that these ghostly particles carry away the energy needed to power a supernova, leaving nothing but a gravitational tombstone behind. What's truly bizarre is how often this might be happening. Surveys suggest up to 30% of massive stars in certain galaxies could be vanishing this way, a revelation that forces us to rewrite the stellar obituary. Traditional supernova, once thought to be the inevitable fate of massive stars, might just be the loud minority, while their silent siblings slip away unnoticed. The implications ripple across astronomy. If phantom supernovae are this common, we may have vastly underestimated the number of black holes lurking in our cosmic neighborhood. It also solves a puzzle: why some supernova predictions fall short. Stars that should have died in spectacular fashion based on their mass might have instead opted for this cosmic disappearing act, leaving telescopes searching for explosions that never came. Perhaps most haunting are the echoes left behind. In rare cases like the object V9 Scorpii, we catch glimpses of the transition, a star brightening slightly as its core gives way, then vanishing into radio silence. These faint death throes, observable only with the most sensitive instruments, hint at a universe where stellar death isn't always a spectacle. Sometimes it's just a whisper, a star folding in on itself with no one but the void as witness. And somewhere out there, another supermassive star might be preparing for its own quiet exit, ready to challenge everything we thought we knew about how giants die. Deep within certain supermassive stars, physics may forge the universe's most extravagant gemstones, cores of crystallized carbon, compressed into celestial diamonds larger than entire planets. These hypothetical diamond core stars aren't just curiosities. They're cosmic pressure cookers where extreme conditions rewrite the rules of stellar chemistry. Imagine a sun-sized vault where temperatures exceed 10,000 degrees and pressures crush carbon atoms into rigid lattices, yet somehow, against all odds, diamond structures emerge like impossible ice sculptures in a furnace. The mathematics behind this stellar alchemy is as precise as the crystals it describes. When supermassive stars rich in carbon near the end of their lives, their cores contract while outer layers cool just enough to cross the phase boundary where carbon crystallizes. Unlike Earth's diamonds formed under mere hundreds of kilometers of crust, these stellar gems endure crushing forces equivalent to stacking 50,000 Empire State Buildings on a sugar cube. The result? A core that's technically solid yet still searingly hot, a paradoxical state where carbon atoms vibrate violently in fixed positions, their rigid arrangement somehow persisting amidst the chaos. What would make these stars sparkle? The answer lies in how crystallized cores interact with X-rays. As high-energy photons from the star's fusion processes strike the diamond lattice, they don't just scatter randomly, they diffract. This organized deflection could create sudden, sharp spikes in X-ray emissions as the core rotates, producing a flickering effect akin to light glancing off a spinning disco ball. NASA Chandra Observatory may have glimpsed this phenomenon in the carbon star B Persei, which exhibits unexplained, millisecond X-ray flashes matching theoretical diffraction patterns for diamond cores. The strangest implication: these stars could be nature's ultimate time capsules. Earth's diamonds trap minerals revealing our planet's history, but stellar diamond cores might preserve isotopes from the universe's earliest nucleosynthesis events. Some models suggest they could even encapsulate exotic states of matter, like metallic hydrogen or quark gluon plasmas, frozen in crystalline cages like insects in amber. Yet the true marvel is how these cosmic jewels might die. When the star finally collapses, the diamond core wouldn't shatter, it would vaporize in a nanosecond, its carbon atoms screaming across the newborn nebula to seed future generations of stars and planets. Every diamond ring on Earth might owe its existence to such an ancient, stellar jewel box meeting its violent end, and somewhere out there, another carbon-rich giant could be forging its diamond heart right now, a hidden cosmic treasure waiting to be found. Hidden among the blazing giants of the cosmos are cosmic archivists, stars so ancient they carry unaltered stardust from the universe's fiery infancy. These celestial time capsules, like the ultra-metal poor star Hy-2301, aren't just old, they're chemical museums, their atmospheres preserving elements forged minutes after the Big Bang. Imagine a stellar vault locking away pristine samples of the early cosmos, where every atom tells a story written 13 billion years ago when galaxies were just beginning to coalesce. What makes these relics so extraordinary is their untouched composition. While most stars recycle material through generations of supernova, contaminating their chemistry, these primordial survivors formed from nearly pure hydrogen and helium, the universe's original building blocks. Their atmospheres contain trace metals at concentrations millions of times lower than our Sun's, like a single grain of salt dissolved in an Olympic swimming pool. The star SMSS J708 takes this purity to extremes. Its iron content is so low that detecting it required analyzing light absorbed by just 30 iron atoms in the entire stellar atmosphere. The hunt for these timekeepers relies on cosmic archaeology. Astronomers use spectral fingerprints to identify telltale patterns of ultra-low metal content, often spotting them in the Milky Way's halo, the sparse outer region where ancient stars avoided galactic pollution. Some, like Hy-140,283, nicknamed the Methuselah star, even clock in older than the universe's current estimated age, a paradox resolved by accounting for relativistic time dilation from their high velocities. But the real treasure lies in their nuclear fossils. Certain isotopes like uranium-238 and thorium-232 act as radioactive clocks, their steady decay allowing astronomers to date these stars with remarkable precision. Hy-123.90, one uranium signature revealed its age as 13.2 billion years, only half a billion years younger than the cosmos itself. Other stars preserve lithium abundances matching predictions from Big Bang nucleosynthesis, offering direct evidence of the universe's first 3 minutes. Perhaps most astonishing is how these ancients continue shaping modern astronomy. Their carbon-nitrogen ratios challenge models of early star formation, suggesting the first stellar generations may have functioned as cosmic reprocessors burning hydrogen differently than modern stars. Others, like STSS J102,915 plus 172,927, defy expectations by existing at all. Their lack of lithium and carbon, implying some unknown mechanism, allowed them to form without the elements thought essential for star birth. These stellar elders aren't just relics, they're active participants in cosmic evolution. Winds from metal-poor stars like Hy-75,240 are currently seeding nearby clouds with barely processed primordial material, offering new generations of stars a taste of the ancient universe. And somewhere in the galactic outskirts, another pristine time capsule might be waiting, its light carrying secrets from a time before time had meaning. The universe has rules most of the time. When it comes to stars, conventional wisdom says their growth should be unlimited, bound only by the gas clouds that feed them. Yet somewhere around 300 times the mass of our Sun, nature slams on the brakes. No star, no matter how dense its nursery or how plentiful its fuel, ever seems to cross this invisible line. It's as if the cosmos has a hidden cap, a celestial speed limit that even the mightiest stars dare not exceed. So what's enforcing this universal weight limit? One leading theory points to the very radiation these giants produce. When a star approaches 200 solar masses, its internal pressure and temperature reach staggering levels, generating photons so energetic they push outward with unprecedented force. At a critical threshold right around that 300 solar mass mark, this radiation pressure overcomes gravity's grip, preventing additional material from sticking to the star. Imagine trying to build a sandcastle in a hurricane. The stronger the winds, or in this case, the star's light, the harder it becomes to add another grain. But radiation pressure isn't the only contender. Some astrophysicists argue that stars destined for extreme mass never get the chance to grow. They effectively strangle themselves in the cradle. In ultra-dense stellar nurseries like the Tarantula Nebula, where stars form shoulder to shoulder, competition is fierce. A protostar aiming for record-breaking size might begin accreting gas rapidly, only for its own ultraviolet fury to ionize and dissipate the surrounding cloud before it can finish feeding. It's the cosmic equivalent of burning through your inheritance before the will is even read. Then there's the fragmentation problem. When gas clouds collapse to form stars, they don't do so neatly. Turbulence and rotation cause them to splinter into smaller pieces like a spinning pizza dough dividing into multiple blobs. For a star to reach 300 solar masses, it would need to form from a cloud so massive and stable that it avoids this fragmentation entirely. The odds of such a pristine collapse are astronomically low, making these behemoths as rare as a perfect storm, yet the most tantalizing possibility involves an even more fundamental constraint, the Eddington limit. Named after astrophysicist Arthur Eddington, this principle states that a star's luminosity can't indefinitely increase without consequence. At a certain point, the outward push of radiation perfectly balances the inward pull of gravity, creating an equilibrium where further growth becomes impossible. For stars with near-perfect efficiency at converting mass to light, that balance tips right around, you guessed it, in 300 solar masses. The evidence hiding in plain sight supports this. Take our 136A1, the current heavyweight champion at 260 solar masses. Nestled in the Tarantula Nebula, it's already pushing the theoretical envelope, glowing with the intensity of nearly 9 million suns. Spectroscopy reveals its surface is so hot that it's literally boiling away, shedding mass at a rate that would vaporize Earth in seconds. This isn't just a star living on the edge, it's a star bumping against the universe's maximum occupancy sign. But what about the outliers? Some models suggest that in the early universe, before heavy elements polluted star-forming clouds, stars might have breached this limit, growing to 600 or even 1,000 solar masses. These hypothetical population Roman 3 stars would have been pure hydrogen and helium materials that absorb less radiation, allowing for more efficient feeding. Yet even if they existed, their lives would have been brief and catastrophic, collapsing almost immediately into black holes and leaving no modern traces to study. The real surprise: this size ceiling might be protecting the universe as we know it. Stars exceeding 300 solar masses wouldn't just die, they'd die spectacularly, likely as pair instability supernova so powerful they leave nothing behind, not even a black hole. The energy release could sterilize entire galactic neighborhoods, disrupting the fragile conditions needed for life. In that sense, the universe's refusal to build bigger stars might be its way of keeping the cosmic playground safe. So while part of us longs for the discovery of a 500 solar mass monster defying the odds, the truth is more profound. Nature has its scales, and even the mightiest stars must eventually bow to them. The next time you look up at the night sky, remember those twinkling lights aren't just stars. They're survivors, each one a testament to the delicate balance between growth and limitation that shapes our universe. From hypervelocity stars rocketing out of galaxies to zombie stars that refuse to die, the universe's most massive stars aren't just defying expectations, they're rewriting the rules of physics itself. We've traveled through 30 of their strangest behaviors: stars that flicker like faulty light bulbs, others that vanish without a trace, and some that spin so fast they stretch into cosmic pancakes. We've witnessed magnetic monsters strong enough to suspend gravity, stellar vampires feasting on their companions, and diamond cores hidden in searing stellar furnaces. Each of these phenomena isn't just a cosmic oddity, it's a crack in the foundation of what we thought we knew, a challenge thrown down by nature to the textbooks gathering dust on astronomers' shelves. Consider the implications. A single supermassive star can warp spacetime, trap light in slow motion, or cough up enough heavy elements to seed future solar systems. Their existence forces us to confront humbling questions. How do magnetic fields grow so powerful they rival black holes? Why do some stars explode multiple times while others collapse silently into oblivion? What quantum quirks lurk in their cores, waiting to upend our understanding of matter itself? These aren't just puzzles for astrophysicists, they're invitations for all of us to marvel at a universe far stranger than fiction. And the wildest part: this is just the beginning. Every discovery peels back another layer, revealing new mysteries beneath. Maybe you're captivated by the rogue stars flung into intergalactic space, or perhaps the stellar phantoms haunting black hole edges. Whatever caught your imagination, remember each of these behaviors started as an impossible anomaly until someone looked closer. That's the beauty of cosmic exploration. Today's head-scratching mystery could be tomorrow's revolutionary breakthrough. So what's your favorite stellar enigma? Drop it in the comments. I'd love to hear which cosmic oddity left you staring at the night sky with fresh wonder. And if you're hungry for more deep dives into the universe's greatest puzzles, hit subscribe, because out there, right now, another supermassive star is probably doing something inexplicable, and we'll be here to unravel it together. The cosmos never sleeps, and neither does curiosity. End scene: subtle visual of a rotating hypervelocity star against a galaxy backdrop, fading slowly as music swells.